Hi everybody. In this video in chapter 2, section 7, we are going to look at things that are not functions necessarily, things that are more generally just equations. These things have really cool graphs. We'll see a few of them. But generally, the things that we're going to look at today are things that are not functions. So in other words, this means that they don't pass the vertical line test. They have more than one output for one input. So far, we have only really been looking at things that are functions. Algebraically, what this looks like is you can write it as y equals, and then some stuff with x or whatever the variable is over on the other side. When you have that type of format, then when you have the graph of that equation, y equals some stuff with only x's, then you will get the graph of a function, something that passes the vertical line test. Again, one output for one input. We haven't really called these explicit functions because we haven't had anything to contrast these with. But now we're going to expand our horizons a little bit further, a lot further actually, and look at things that are just generally equations that may not represent a function. So these are called implicit equations, or the process that we'll use calculus on them with is called implicit differentiation. So just to give you a little bit of a sense of what these kinds of graphs might look like, again, we'll see a few of them. We have things that are circles. Make believe that that is a better circle. This is something that definitely fails the vertical line test. We know that the equation for a circle is x squared plus y squared equals radius squared. So this isn't written in the form y equals. We also have kinds of equations that might look like this, like a circle, but with caved in a little bit at the origin. And this is called a cardioid because it looks like a heart. Obviously, this fails the vertical line test, but it still has a graph, and we can still write down an equation for it. It just won't be in y equals form. We can also have a graph of an infinity symbol like this. This is called actually a lemniscate. That's the fancy math word for that. Again, this fails the vertical line test in multiple spots, but it still has a graph, and as we'll see, these things still have slopes of tangent lines, which is what we're going to be interested in. So just to, again, give you like a sense of what the difference is, I've got some examples here. So let's look at the equation x, y equals 1. So the way this is written, this is in what we would call an implicit equation. This is a simple one because we can solve it for y. We can get y alone on one side of the equal sign. So in this simple case, we can solve it for y. Right, that would just be dividing by x. So we'll get y equals 1 over x, or x to the negative 1. And this would be an explicit form. Because we were able to solve this for y, we have a nice, neat packaged formula for y with just x's plugged in on the other side. Then, since this is calculus and we're finding derivatives, we can even differentiate this. And we haven't been calling it explicit differentiation, but I guess that's really what we've been doing. So we can differentiate this explicitly. So we find the derivative of y, which we would call dy dx, or y prime. And that would be negative x to the negative 2, or negative 1 over x squared. So things that are explicit to start have explicit derivatives. Okay, there's only x's in them. As we'll see, things that are implicit will have lots of x's and y's kind of mixed up together. The second, I guess the first even kind of simple equation that doesn't give rise to an explicit form or an explicit function would be something like a circle. So let's just look at the unit circle. Here's a nice one that I had my iPad help me make a perfect circle. So here's the graph of the unit circle over here. And the radius of the unit circle, right, just to make it a little more specific here, right, we've got 1, 1 all around, so that's -1, and that's -1 down there. Right, so the equation for that is x squared plus y squared equals 1. This is also an implicit equation. Notice I'm calling it equation because it's not a function. We reserve function for things that are functions, so this is an implicit equation. If we try to solve for y here, we can almost do it. We can get really close. So if we have x squared plus y squared equals 1, we can subtract the x squared from both sides. But then when we apply the square root function, or the square root to both sides, we get a plus and a minus out when we apply square root. Because when you square positive or negative, you'll get the same result in the end. So when we take the square root, we have to go both ways. So this is going to actually give rise to 2 different functions. Let's move this over for a sec. So we'll get the positive square root of 1 minus x squared. We also get the negative square root of 1 minus x squared. So this, how is this connected to the graph of the circle? Excuse me. So the first one, the square root of 1 minus x squared, that's actually the top half of the circle. So that part represents just that top half, which in and of itself is a function. And then the negative is that flipped over across the x-axis. So this is the bottom half of the circle. So that's this part down here, which on its own is a function. So, but it's it's not as nice to have this collection of 2 parts as it is to just have this equation here that is just nice. Like you just need one thing to describe the circle instead of 2. But I just want to show this to you to kind of, I don't know, give you a sense of why implicit differentiation is better, because we will find the derivative of this implicitly. Let's go through it explicitly first. So basically that's just the old way that we know how to find derivatives and such. So we can then differentiate each of these halves separately. So this question isn't like asking us for anything. I'm just trying to give you a sense of like, how we might go about this using our old methods, so we can compare to the new method of implicit differentiation, and hopefully, it's a lot less work. So we have the top half here. So this would be the positive root. So to differentiate this, we'll rewrite this as 1/2 power instead of square root. And then to find the derivative here, we need the general power rule, because we have some stuff raised to a power that is more than just x to a power, right? Overall, we've got some stuff here, 1 minus x squared, all raised to the 1/2 power. So that's kind of the structure of the function. So when we find the derivative, we'll bring the 1/2 down, multiply by the inside, and then subtract 1 from the power. Right, so remember the base stays the same when we use the general power rule. We still bring the exponent down, multiply, and subtract 1 from the exponent, but then we have to go inside, this is the chain or the layering part, and multiply by the derivative of the inside, which is the derivative of the base. So that'll be minus 2x. And if we just simplify this a little bit, we can divide the 1/2 times the -2. That'll give us -1. Then we've also got x. And then the exponent of -1/2, we can move all that stuff down in the bottom and make it a square root. So -x over 1 minus x squared. We can also do that in the denominator all right, in the bottom part, the denominator of the circle, the bottom half of the circle, we can find the derivative there as well. So here it's the same thing, except we have a negative in the front. So we still want to rewrite this. We'll just have a negative in the front of the whole function. When we find the derivative, again, we're going to use the general power rule. So we'll have negative 1/2 in the front. By bringing that exponent down, we'll still subtract 1 from the power, and we'll still multiply by the derivative of the inside, which is still negative 2x. Then the negative 1/2 and the negative 2, they multiply to positive 1 this time. So we'll have positive x up top. And then we'll bring down the 1 minus x squared to the denominator and maybe rewrite it as a square root. So we have these derivatives here. You can use these to find the slopes of the tangent lines. So let's just take a second to remind ourselves how to do that. I'm going to move these guys over just so we have a little more space. Okay. So looking at the top half here, just at some kind of simple points. So if we look right here, this has an x value of 0. Okay, this point here is 0, 1. And if we plug in a 0 into the derivative, hopefully we'll get 0 out because the tangent line here, right, is horizontal. So it should have a slope of 0. When we plug a 0 in for x, we get negative 0 using this derivative here because we're working in the top half. So we'll get negative 0, which is just 0, over the square root of 1 minus 0 squared. All right, that's 0 over the square root of 1, which is 0 over 1, which is 0. Okay, so like this all works. We also have some places that, over here, where we'll have a vertical tangent line, and also here, these points are 1, 0 and negative 1, 0. Here we should have a derivative being undefined because vertical lines don't have a slope. And if you take a look at what happens when you plug an x equals 1 or negative 1 into the derivative, you're going to get a 0 in the bottom. Right, we'll square 1, that gives us 1. We subtract 1 minus 1, that gives us 0. The square root of 0 is just 0, and so this is undefined. Same thing with negative 1. When you square negative 1, you also get positive 1. And so, oh wait, I think I have negative 1. So this should actually be in the numerator here a positive 1. Right, because we're negating the x up top. So negative 1 would turn us around to being positive 1. And so again, that's undefined. We could also do this at other points too. So if you plug in right here, say a half, here we'll have a tangent line that looks something like this. And the slope there, if we plug 1/2 in, you'll find is negative 1 over root 3. So, I mean, just showing you and reminding you a little bit about how we use derivatives, what they're for, all this stuff. Nothing new here, really. And this also works in the bottom half as well. So we can have a horizontal tangent line right here, right? That would be at 0, negative 1. And when we plug a 0 in for x into this derivative now for the bottom half, we'll get the same thing. I don't know where that extra parenthesis came from. So it'll be 0 over radical 1 minus 0 squared, which is 0. And you also get the same things at the other places, right? We'll have a vertical tangent line here, a vertical tangent line here. You'll get undefined derivatives at those two spots as well. And you can find the slopes at the bottom part. You just need the bottom derivative. So again, this is nothing new. This is our old stuff. But the point is that this was like, I don't know, it's like a lot of work to do all of this. So I'll show you in just a minute how to find the derivative of this a little more simply. Here's an equation, x squared y minus 6x cubed plus 2y to the 5th equals x plus 3y. This is for sure an implicit equation, right? There's no y equals with only stuff with x on the other side. Basically, the variables are not separated. They are all mixed together. We've got a y here we've got a y cubed here, we've got a y to the fifth, and we've also got a y here. And you could try all you want to solve this for y on one side, but you won't be able to do it. So in this case, we just cannot solve for y. We cannot put this into an explicit form. And there are a lot of things like this kind of an equation. So it's worth our time to try to figure out how to find the derivative and the slope, because these graphs still have slopes of tangent lines. Okay, so the idea here, or what implicit differentiation is that whether or not we can convert an implicit equation into an explicit function, it doesn't affect our ability to find the slope or dy dx of the curve, thankfully. Don't worry, I'll tell you all about how to do it. This process of finding dy dx for an implicit equation is called implicit differentiation. So before we go on to finding dy dx for an entire equation, I'd like to just take a few minutes to see how we might just handle each of the terms that we might encounter in an equation. Right, all of our differentiation rules that we know and love and appreciate so far still apply. So if we're going to find the derivative of this equation, for example, we have different terms here that will be able to separate because they're separated by plus and minus. And so we want to figure out how we will handle something like this, or something like this, or something like this, or this, or this. Right, some things already, like this x here, we know how to take care of, but things with the y's are going to be a little bit different. So let us differentiate each expression with respect to x. Okay, so again, these aren't equations, these are just parts of equations that we'll encounter. So to start, if we differentiate in example 1, x cubed with respect to x, the way that we would write that is we have, so the with respect to x, I'll just make this a little clearer here, with respect to x, what that really means is you're finding the derivative d dx. So d dx is what we're going to be putting like kind of in the front of the expression that we are finding the derivative of. Okay, there we go. So d dx of x cubed. We haven't really had to pay too much attention to this until now. So that's okay though. Now that we have all of our rules under our belt and we're comfortable with them, we can add something a little bit extra. So this is just 3x squared, right? We all know how to do that, hopefully. So 3x squared derivative, or x cubed derivative is 3x squared. Nothing fancy or special or different about that in this case still. The next one is d dx, or the derivative of y cubed. Y cubed this time, instead of x cubed. Okay, now here the variables have always matched for us. Like the dx part here is always the x that we're differentiating. But if we think for a second about how, what we're really doing on the left-hand side of, say, something that's like y equals, I don't know, x cubed, how about? When we take the derivative of both sides, we are really like kind of applying like this derivative process to both sides. We don't really write it. We normally just skip straight to saying, oh, hey, this is y prime on the left. But really, that's the derivative of y. That's what we're saying. So we just write dy dx or y prime. And then we differentiate the right-hand side, and we just, don't have to do anything, like think about what's going on the right-hand side in terms of the dx, really. So what I'm trying to point out here is that we've been differentiating y stuff all along, except it's only been y to the first. And the derivative of that we just say is the symbol dy dx, or y prime. So we can use y prime here if you prefer. Okay, so now when we're differentiating y cubed, well, it's just a little different, but it's related to both this idea and this idea. So when we differentiate x to the third, we get 3x squared. When we differentiate y to the third, we also get 3y squared. But here, the y, the base that's raised to the power, isn't x. Obviously, it's different. And we have to take that into account. It's just going to be something that's different. Like, we have to consider that the base here is y. And so if you think back to the general power rule, where we had the derivative of a base to a power, right, where this base is some stuff with x, and we're differentiating with respect to x. So maybe it's like, 1 minus x squared to the 1/2. We want to find the derivative of that. Okay, the rule said bring the power down, leave the base the same, subtract 1 from the power, then multiply by the derivative of the base, right? So we just differentiated this example down here a couple minutes ago. So we bring the 1/2 down, we leave the base the same, subtract 1 from the power, and then we multiply by the derivative of the inside. Now here what we have is this 1/2. Wait, no, the 1 minus x squared, sorry. The 1 minus x squared, this is really y. 1 minus x squared. Okay, we're really like just gonna replace that with y. So then this negative 2x, we could find that formula for the derivative of the base because we had an expression for for y in terms of x, but here we don't. So this is just going to be y prime or dy dx, because ultimately this is what we're going to be looking for. So basically what I'm trying to say, in hopefully a sort of clear way, but it might be kind of roundabout, is that when we differentiate some stuff with y with respect to x, then we find the derivative like normal, but because of the general power rule, we're missing this piece here, which would just be y prime or dy dx. So anytime that we differentiate some stuff with y with respect to x, we have to multiply that term by the derivative of y, which we don't know what it is, so we just use the symbol dy dx or y prime. And so that's the derivative of y cubed with respect to x, 3y squared times dy dx. All right, let's look at another example. How about 3 over y squared? Over y squared. Okay, so all of our rules that we know and again have used with x's still apply here. So I would suggest that we rewrite this without a fraction. 3y to the negative 2. Okay, then we go ahead and find the derivative, basically as if it were 3x to the negative 2. And so that'll be negative 6y to the negative 3. But then that's only this part of the general power rule. We need to multiply by the derivative of the base, which is y in this example. And so we just have to multiply this by y prime, or I'm always going to use dy dx. I can rewrite this too. We could say this is negative 6 over y cubed times dy dx. All right, example number 4 is 4x squared plus 2y. Okay, we're differentiating this with respect to x. So d dx of 4x squared plus 2y. Okay, so here we have a mixture. We've got a 4x squared plus a 2y. And when we are differentiating a sum or a difference, we can find the derivatives of each of the individual things that make up the sum or difference. So if this helps you, we can write this out like this is the derivative of 4x squared plus the derivative of 2y. But if you just know that, hey, I can take the derivative of each of these pieces separately, then you don't have to write this part out. But we all learn in different ways. So 4x squared's derivative, that's 8x. Nothing special with anything x related. Then the 2y, the derivative of that is just 2. Right? We just differentiate it as if it were 2x. So the derivative of that would just be 2. But we differentiated a y term here. So we have to multiply this 2 and only the 2 by dy dx. So that would be the derivative of that piece. All right, we got 2 more here. We've got xy and then 4x cubed times y squared. Okay, let's just move this up here really quick so I can still see our questions. So we've got in number 5, the derivative of x times y. All right, this one is different than 1 through 4 in that we have a product here. We've got a product of 2 variable things. So this is going to need 100% of the time the product rule. So let's make a little note of that with like a star here because it's kind of easy to miss. The x times y is very different than just x by itself or y by itself. Here we need the product rule. So we need to use the product rule whenever anything with x and anything with y are multiplied. Anytime, even if it's different powers, not just x times y, even if there's a number in the front, you have to use the product rule if you want to find the derivative correctly. Okay. So the product rule, I think we use like u and v, right? So let's get some of that stuff going on here. So I would call u equal to x. I would call v equal to y. Why not just get more letters involved, right? U equals x and v equals y. Then in the product rule, we need the derivatives of each. Okay, so u prime, the derivative of x, we're differentiating with respect to x. So its derivative is just 1. V prime is the derivative of y. Here is where we need the implicit differentiation process because we are finding the derivative of y term, but it's with respect to x, dx of the entire thing. So the derivative of y will be 1 as well, but this 1 needs to be multiplied by dy dx. 1 times dy dx is just dy dx, so we can rewrite that. Okay, now putting this all together into the product rule, we get the first times the derivative of the second, so u times v prime, so it'll just be x times dy dx. Then we add the second times the derivative of the first, so v times u prime. So it'll be y times 1, or just y. We can just write this as x dy dx plus y. And there's the derivative of that thing, right? So we have first x, the derivative of the second, derivative of y is dy dx. Then we add the second, y alone, times the derivative of the first, x. And because we didn't differentiate a y term in this second part here, right? The derivative of x was just 1. There's no dy dx on that part. Okay, example number 6 is 4x cubed times y squared. 4x cubed times y squared. All right, so here again, we have another product. So we have to use the product rule on this one as well. So I encourage you to just pause this and see if you can put together the product rule, at least get it started. So I would say we'll group the 4 with the x cubed. So I'll call that one u, and then I'll call v the y squared. Okay, then u prime, that derivative will just be 12x to the second. Okay, no dy dx because no y's were differentiated in that part. V prime, though, we are going to differentiate some y's, right? Y squared's derivative will be 2y, but then we need times dy dx. Now, piecing this together into the product rule, we will get 4x cubed times 2y dy dx. That's u times v prime. Then we add v y squared times u prime, which will be 12x to the second. And it's really helpful, I think, if you just stop and try to like visualize what's happening sometimes. So I like to just visually see, is my product rule, does it look right? So like looking back just here, I've got the first time, that's good, times the derivative of the second. Okay, y squared's derivative is 2y dy dx, plus I leave the second one alone, and then multiply that by the derivative of the first, and that's 12x squared. So I don't know, I think that relying a little less on like symbols and stuff, the more that you work on calculus can be really helpful. But they're a good tool for learning, so if we want to write the u and the v down, that's totally fine. Simplifying this, we can do the 4 times the 2, that is 8. So we'll get 8x cubed y times dy dx. And then we normally just write the x's in front of the y's, so we'll just write that as 12x squared y squared. Numbers, then x's, then y's. Okay, so again, these are just the pieces of the equations that we're going to see in the next video. We'll actually find a formula for dy dx for a whole equation. So here we haven't solved for dy dx, it's just inside of the derivative of the expressions that we have. So we'll go through that in a little bit, but I'd like you to, in the meantime, before you watch the next video, just try your hand at these 4 examples here. Make sure that you have the basic idea of the implicit differentiation process. And when you're all set with these 4, you can tune into the next video and we'll find some implicit derivatives.